Today we're going to be building an ecological trap model featuring the veery. Jed introduced us to the veery, and you now know that it's a long-distance migrant. Let's take a look at the map. It breeds in the northern portion of North America, and it winters in South America, a fairly big expansive range. During migration it can be seen along the eastern portions of Latin America, as well as most of the eastern portion of the United States. Let's keep this map in mind while we now look at the life cycle of the veery. We'll start off with a chick that's being born in the North American breeding grounds. That chick then leaves the nest, matures a bit, migrates to the wintering habitat, and spends the winter in South America. After some period, it migrates back to North America, and then, at that point, it needs to make a decision about where it will breed for the very first time. This individual is called a recruit. It was born the year before, but it's been recruited into the breeding population. And this decision about where to nest is controlled by this parameter called alpha. In our model, we'll have two choices. It can choose to nest in a core habitat, or it can choose to nest in a forest edge habitat. Then, once it chooses a habitat, it settles down and establishes a territory, claims its territory, and begins singing. The males and females pair up, and that often is the time when we census these songbirds because they're very vocal and they're easy to count at that time. Then they reproduce and have young, and the cycle continues. There are a few things in this life cycle you need to keep in mind. The first thing is that this is an example of a pre-breeding census. We count the birds, the adults that are on the breeding ground. They've just landed on their territories and are singing, and then they have offspring. So we're not actually counting any chicks. We're just counting adults. And the second thing to keep in mind is that this model represents a female model. We're going to just focus on the females who make the choice of where to breed, even though we usually count these birds by listening to singing males. We're going to assume that all of those males are mated and have a female, so we're really interested in the female portion of the population. And once again, we're interested in primarily those individuals that were born in a time step and then become recruited into the breeding population as breeders in the next time step. Those are the key animals that will be making a decision about where to breed. We're going to assume that once they have secured a spot in either the edge or the core habitat, then they'll continue to remain in that habitat for the rest of their life. Alright, now let's go ahead and hide this cycle, and we'll go ahead and enter the parameters for this model. We have our core habitat parameters in columns B through F in row 8, and then in row 9 we have the parameters for the edge habitats. We'll let the birth rate for the core be 0.5 and the birth rate for the edge be lower at 0.3. We'll let the juvenile survival rate be 0.5 for each. And let's take a look at what that means. You have some individuals that are born, and a juvenile survival means that there's a 50% chance that they'll make it to become adults to this particular spot and able to make this territory selection in the next year. The adult survivorship will be quite high, 0.8 and 0.8, and that represents the probability that an adult that was counted at this particular moment in year t will be alive to be counted in year t plus 1. So each individual has an 80% chance of making it back around the horn. This attractiveness parameter ranges between 0 and 1, and we'll set that at 0.8, and then in cell E9 we'll let that be 1 minus cell E8. And this represents how attractive the core is and the edge is when these birds are making their selection. So in this example, if we have 100 individuals that are born and 50 of them make it to this recruit portion right here, then 80% of those 50 individuals will try to secure a breeding territory in the core habitat, and 20% of those individuals will try to breed in the edge habitat. That would be their first choice. So this attractiveness is very much about choice. Now they won't all get their choice because these two habitats have a carrying capacity, and that's represented by K. Let's assume that there are 25 breeding spots in the core and 40 breeding spots in the edge. Now we went through those a little quickly, but I'm trusting that you paid close attention to Jed's explanation of these and calculations of these numbers. So at this point we can start building our model. Let's begin by assuming that there are 15 females in the core habitat and 10 in the edge habitat. Down column R, that gives us our total. We've got 15 plus 10 birds, cell B15 plus cell I15, and that tells us that our population right now consists of 25 females. Where are we in the cycle? We're right here. We're doing our census. The birds are counted. It's a very small window. These individuals are counted, and the next thing to happen is they will produce young. So let's do that. How many births should appear in the core habitat? Right, that's going to be the number of breeders in the core habitat times the per capita birth rate for the core habitat. And we'll anchor that cell, and we'll do the same thing for the edge. The number of births that come from the edge habitat are the number of breeders in the edge habitat times their per capita birth rate. That's where we are. The young have been born. Now we need to know the total number of young that have been born, and the total of these individuals that can select a breeding territory in the next time step. So this is all being carried out. We're still within our first time step, and then when we do the census, they'll advance to the next time step. So let's calculate our total births, and we'll do that in cell P15. That's simply C15 plus J15. And this represents the total number of individuals that are produced in our whole system. Now, how many of those individuals will make it to become recruits? It's going to be equal to the births from the core times the juvenile survival rate from the core, anchor that, plus the births from the edge times the juvenile survival rate from the edge habitat, and we'll anchor that reference. Right? So of these 10.5 births, 5.3 individuals will become recruits. So we're right here. 10.5, 5.3 make it to this particular place where they want to select a breeding territory. So now we can enter in equations for the recruits in the edge habitat and in the core habitat. And you'll see that we've broken this out into 4 different pieces. the potential recruits, the ones that want to breed in the core, the successful recruits, those that actually will secure a territory in the core, the unsuccessful recruits, those are individuals that want to reproduce in the core but can't because we've run out of breeding sites. And then the final, total number that actually are recruited into that particular habitat type. So what would the potential number be? Well, if you're thinking it has something to do with alpha, you're totally correct. The potential number is going to be the total recruits times alpha for the core, and we need to anchor the reference for alpha. And the potential recruits into the edge habitat are going to be the total recruits times 1 minus alpha, and that's stored in cell E9. And we'll anchor that as well. So all we're doing here is partitioning these recruits into the places they want to go. There's 5.3 total recruits, 4.2 want to go into the core, and 1.1 want to go into the edge. Now, how many of these will be successful? And here's where things get a little tricky, because we're talking about individuals like right at this margin here. This is the place where we begin to census, and we're making our decision about where to land right before the census. And we've made a key assumption that breeders that are in the core, these are adults that are currently in the core, won't move. They're going to take up some space there. So at this point, it's fruitful for us to go ahead and calculate how many of those slots are taken by the returning adults. So what would that be? That's going to be equal to the number of adults in the core times the adult survival rate for the core, anchor. And for the edge, it's going to be the number of adults in the edge times the adult survival rate for the edge, anchor that. So we're down now to how many of these potential recruits will actually secure a spot in the core, and how many will actually secure a spot in the edge. Let's start with the core. We want to know, of these 4.2 individuals that want to settle there, how many will actually secure a territory? Well, what kind of logic do we need? We know that the core has 25 breeding locations, and we also know that 12 of those will be taken by the current adults that will return next year. We know that 4.2 recruits want some spots, and so our equation that's going to be entered into cell F15 needs to consider the carrying capacity, the returning adults, as well as the potential adults. Let's give this a try. We'll use an if function. The if function has 3 arguments. The first argument is the logical test. The second argument is what you want the spreadsheet to return if the logical test is true. And the third argument is what you want the spreadsheet to return if the logical test is false. Here we want to know how many recruits would be successful. So our logical test is going to be something like this. If the number of adults that survived and returned to the core, that will return to the core, plus all these potential recruits that want a place in the core habitat for breeding, we want to know, is that less than or equal to the carrying capacity of the core? And you'll see that Excel is returning the word true. So the spreadsheet will return whatever we put into this next box. So if we are below carrying capacity, then of course all of these individuals, these potential individuals, will secure a breeding spot. If not, though, if we're going to overshoot our carrying capacity, then what we need to do is just account for those spaces that are not occupied by returning adults. So that's going to be equal to the carrying capacity minus the adults that return and survive. So the argument, the whole if function says, really is asking, are there enough slots, territories, empty territories in the core habitat after we account for these returning adults? And given that there are only 25 breeding territories possible. If there's enough room, bring them all in. If not, though, bring in as many slots as available. That would be 25 minus the returning adults. Make sense? So the next column should be a snap. Here's the number that wanted to acquire territory in the core. Here's the number that were successful. How many were unsuccessful? It's just going to be the potential number minus the successful number. At this point now we can do the same exercise for the edge. Go ahead and put your video on pause and enter those equations, and then we'll enter them together when I come back.